So I'm Carson. I'm with the textile team and Tableland, and we're one of the sponsors. And when we were talking with Boris about what we wanted to do for a lot of these sessions, a big kind of goal was to help teach some of the Dev Connect community about IPFS things. And we've been doing lots of IPFS things this week. And so this is a talk kind of about one of the little things, arguably one of the more important things about IPFS, which is how we actually build up that content addressed data. And so I'll talk a little bit about that and how easy it is to start doing a little bit more sort of low-level structured data for like building dApps and applications and things like that. So this is it's a session for I mean this in the nicest way, noobs to the IPFS space who are starting to get a little, dig a little deeper into what it is that IPFS is. So, at the end of the day, the internet is pretty much just about, well, it's as we all know, it's a series of connected tubes, but it's all about links. And when you're building websites, it's links to web pages, and when you're building links to other websites, and we create this, web of information. And the new version of the internet that we're building with IPFS is no different. It's all about links. It's just instead of telling you where to go fetch that something from, we're going to tell you what that thing that you're going to go fetch looks like. So we use content addressing for that. But it's at the end of the day, it's all about links. And those links are defined by a data protocol called IPLD. And so this stands for interplanetary linked data. Everything has to start with IP, and then you get to call it something else towards the end. So interplanetary linked data. And if you've been around the internet for a while, you've probably heard about linked data. And IPLD is probably the most practical implementation of open linked data out there. It's very simple, and we're going to talk about how you kind of get to that simple data representation over the next couple of slides. But the whole idea behind IPLD and IPFS is to make a better, more connected internet. And we want that connected internet to actually consistently work, even when links start to die and all that stuff. And last night I was talking to some folks that are familiar with Internet Archive and a lot of the archiving and maintaining of information on the web. And we're still at a point where the average web page, lifespan of the average web page is about 90 days. After that, links to it expire, or it stops getting hosted, or you just can never access it anymore. IPFS is a lot about just sort of making those links permanent to the content that it was at some point. Hey, maybe it won't be hosted anymore, but at least things that depend on those links will continue to function and behave and operate the way that we expect them to. So a more resilient and connected internet comes out of that. And so IPLD is a core component of IPFS. And so, okay, what the heck is IPLD? Really, it's just a pretty simple data model for distributed data structures. And that is just a sort of slightly nerdy way of saying it's just a data model for linking data. And it is the core piece that we use to build up our content addresses, our CIDs, those BAFI numbers that we were talking about at the beginning of the day. It's the core piece that we use to build that up and to actually then calculate what is the CID for my particular piece of data. And so we use IPLD and CIDs to do that. That's great, and that's very simple. And if I want to add a file to IPFS, all these things are all happening in the background. IPLD is being used in the background. But it is also, you might call it like a gateway drug to way more advanced operations over the decentralized web. So once we get a handle on what IPLD is and how we can use it and what it's useful for, we can start to leverage it to do a lot more clever things. And I'm going to try to elucidate what those clever things are over the next couple of slides. But it's a way to help us build more advanced applications on the decentralized web. And there are a couple of core concepts that we care about when we're talking about IPLD. As we mentioned, the most important thing about IPFS is it is the content addressable web. It's all about content addressing. And so in that case, data whether it's a web page or a picture of your cat or a blog post, whatever, the data is identified by what it is, its content. And I'll talk about how we actually calculate its ID from the content in a little bit. And it's about links. So IPLD, linked data. It allows linking bits and pieces of data to other bits and pieces of data. And then through all of those linking, we get this idea of like immutable data structures. So we get these like static, immutable data structures. And I do want to take some time for a second to talk about what I mean when I mean immutable. Sometimes IPFS has been referred to as like the permanent web, or like an immutable web. And that is true, but it's also misleading. Immutable just means that once I've created some version of the data, that version is going to be valid and immutable and unchanging for the rest of time. But that doesn't mean that the sort of like semantic information that data represents is immutable. We can have like dynamic web pages built on immutable data, and so it's a little bit misleading to call IPFS the permanent or immutable web, but that's what we're talking about when we talk about it. And a big piece of what we get from immutability is interoperability. And IPLD has this concept of like data interoperability built in as a core piece. So IPLD can represent all sorts of things that you care about as a like developer or a programmer, like lists and trees and graphs and raw values and things like that, as well as links between all of those different things. And so you can interoperate between IPFS, different blockchains. You can actually use IPLD to parse Bitcoin transactions. And you can actually serve Bitcoin transactions over IPFS because you can interoperate between these data structures. So it offers this like sort of super duper powerful interoperability layer that almost nobody coming new to the ecosystem really gets exposed to right away. So hopefully that's what we'll do today. It also simplifies that interoperability so that there's very few decisions that you need to make about like how I'm going to do this. So if I want to sort of parse the Bitcoin blockchain or data structure over IPFS, then there are very well-defined ways to like encode and decode those data structures so that an IPFS gateway knows how to and can understand how to move through the graph of updates or the chain of blocks, if you will. So it's all about interoperability, and IPLD is well defined by a spec. And naturally, everyone will want to read that very technical spec in order to fully understand it. And that was a sort of cheesy joke, but like there is a spec defined there, but nobody expects you to read that specification. It just outlines all of the very powerful and important things that we can do with IPLD. But the beauty of it is, of course, it's a piece of technology with a specification behind it, and it's built into a lot of the tooling that you may use when you're working with IPFS. So IPLD is built into IPFS. It's built into Filecoin. It's actually built into lots of other protocols that operate in the decentralized web. Some chat-based protocols, some like data storage protocols, like Ceramic uses IPLD. Textile, my own company, uses IPLD. Lots of different chat apps and things like that represent data using these linked IPLD graphs. But obviously IPFS is the most well-known example of this. And the way that IPFS leverages IPLD, kind of the most obvious or first way that people experience it is they want to do something like IPFS add my data, right? You want to add an image or something like that to IPFS. And you would use the IPFS command line tool maybe to do that, or you would use a JavaScript SDK or a Go or whatever. And what is actually happening in the background is that a bunch of work is happening to take that data, chunk it up into chunks, build those chunks up into a graph, which is an IPLD structure, and then calculate a CID from that and pop it back to you. And I'll show you kind of what I mean about building up a graph or DAG in a second. But all of that is happening kind of in the background when you're using IPFS. And years ago, we wrote a bunch of blog posts about like what's really happening when you add data to IPFS. And those are good reads, but in the next couple slides, I'll kind of summarize that in a much more approachable way. But once you get a handle on how IPLD works and how it is this sort of key component of content addressing on IPFS, then you can start to use it directly and build much more advanced data structures and much more advanced sort of data models for your applications so that you can optimize things that you care about, like even help you optimize page loads so that when you load, I don't know, you're building a video platform, you don't accidentally try and load like all the videos all at once. Instead, you load links to those videos one at a time. So there's a couple of things that I kind of want to mention, right? The first thing I said was that IPFS takes the data, chunks it up, and builds a graph. And what it's building is something called a Merkle DAG. So first of all, a DAG is a directed acyclic graph. It's just a tree structure where there's no loops back on itself. Okay? And that's a pretty important property because it means that we can actually calculate a single content addressed at the root of that DAG or data structure, and we can use that to sort of pass around and represent a reference to this data that we're talking about. Each node in this graph is a hash of its own data, or of its data, and each node has links to other nodes, and we build this up to build a tree, and it looks something like this. So at the top, we have this like root hash, and in the intermediate nodes, this is a sort of hash of the data below it until we get to the chunks. So in the case of IPFS, we actually say take a cat photo, we break it up into sort of specific chunk sizes. That's those data 0 through 3. And then we start to kind of build those together to build this data structure. And then what you pop out when you type in IPFS add is that root hash at the top of the tree. And then you could basically say, okay, I'm going to add that to IPFS, and then you email your collaborator over your image or something like that, and you say, hey, this is the data that I'm working with. Here you go, and you send them a little Baffy blah 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 string. It's like 42 characters long, and it represents an entire image. This is pretty great. And what actually this is an IPLD structure with a root hash at the top, and it has internal links. So this is linked data. In this case, it's sort of like kind of opaque what it does. It's just one, really, you care about the picture. It's one picture, and it's broken up into little bits. But we can also make those links sort of have semantic meaning as well. So maybe you have a data structure where, like your profile photo is a link to an IPFS hash like this. And so you can start to get a little bit more nuanced in what you actually represent with data. And so you might call that process of taking the data structures that you're using for your application, maybe it's like user data or some JSON document that represents your user, and turning it into an IPLD DAG, we might call that process Merkleization. And that's like not a real word, but it's a good sort of descriptor of the process of taking a normal data structure like JSON or a list or an array or whatever, and designing it in such a way that we can create a DAG from that with links and things like that. So the idea of Merkleization is just we turn certain kinds of data structures into a hash-linked data structure that's compatible with IPLD. And ideally, when we do this, we don't use our brains to actually have to think about this. It should just happen really automatically and easily. And pretty much all we need to do is we just replace pointers in our data set with hashes or pointers to hashes of other things. And that's pretty much it. So I'm going to try and show some examples to illustrate this a little bit better. So imagine we have this very simple JSON data structure here where it's an object, it has a pointer to some other object. In this case, it's an object that has a hello key, and the value for that key is world. Okay? Now, we could do something way more complicated. Like instead, it could be a JSON document that represents a user in our dApp. And so I don't know if anybody here is going to be hacking in the ETH Global Hackathon this weekend, but you're probably going to have some kind of data structures that represent users or represent information, and it might look something like this. Okay, so we will use an example straight from the sort of Helia implementation. So Helia is a JavaScript implementation of IPFS. You may be familiar with it. If you're building like an application or a DApp or something like that, it's probably the first thing you're going to reach for. And it's pretty easy to use nowadays. And so here's an example of how you would do that. So you would, npm install Helia, and you import it, and you're going to create a Helia node. That's basically saying I'm going to create an IPFS node. And in this case, I want to be able to add some JSON data to it, sort of semi-structured JSON data. So the first 4 lines of code there are pretty much just setting that stuff up. And then what I want to do is I want to add my data to IPFS. So j.add, and I'm going to add the whole data structure to IPFS. And I get back that root CID that represents that whole piece of data. And if I then go and fetch that from IPFS, I get back the thing that I created. Wow, okay, IPFS sort of works. That's great. So far, I haven't taken any advantage of the fact that under the hood, this is all a linked data structure. Right now, I've just basically created one little bit of data that has a link to something that I already defined, a JavaScript object. So we've still got pointer is a pointer to an actual object. So what we can do is by adding one little step, we replace our pointer with a hash or with a link to the underlying data. And again, this is a sort of like, I don't know, you wouldn't really necessarily need to have a pointer to like a tiny JSON object that says hello world, but it illustrates the point fairly nicely, which is, okay, what I'm going to do is I'll add this first object, hello world, to IPFS, and I'll get back an immutable CID or address that represents that underlying data. And then I'll create a new object, and I've replaced the direct pointer to that data with the hash, the CID. And then I'll add that object to IPFS. And then what I can do is go and I'll fetch that back again. And what I get back is an object where pointer points to a CID, a content address, that represents a reference to the underlying IPLD data. And then I might take that CID that I get and go fetch that thing in order to actually get the underlying hello world thing. Now, replace hello world with link to an image or a profile picture or something like that, and you can start to see why this could be potentially useful when you're talking about user data. Because I don't necessarily want to go and fetch user data if it has a bunch of images in it. If I'm on a given page load, I might not actually need that image yet. Right? So you can start to imagine that I can hyper-optimize my data structures in my application so that I can fetch the data only when I need it. But the whole entire data structure references all of the things that I could potentially need for my user all in kind of one place. And so you can sort of start to realize you can make sort of very lazy data structures. And this is just the default simple IPFS API. And in this case, I'm just interested in like JSON data structures in this particular case. JSON data structures with links. But there is so much more that you can do with IPLD if you want to start paying attention to actually creating these links and things. And another key piece of IPLD, something that's quite important, is it provides canonical encoding for the underlying data, so that when the an IPFS gateway goes and fetches data for you, it knows how to decode that and show it to you in a way that you're expecting. So that if you create the same JSON object and calculate its IPLD structure, calculate its CID, no matter how that thing is defined, you're always going to get back the same CID. And that's kind of an important feature of the decentralized web, is in addition to being like sort of hash-linked data, we also want those to be deterministic hash-linked data structures, so that when I ask for something, I get back what I'm expecting. And so IPFS has sort of built-in assumptions about how you want to interact with IPLD, but all that underlying IPLD stuff, you can have access to that directly. And so actually at Textile, we spend a lot of time working with like IPLD and libp2p and some of the underlying libraries that are used in IPFS, but I rarely actually interact directly with like Helia or Kubo or any of these common IPFS implementations. often I reach directly for the underlying piece of tech that I actually need. In this case, we're talking about IPLD. And I'm using the JavaScript APIs and libraries because that's what a lot of DevConnect developers are interfacing with, and so it's useful to have that type of example. But here is me interacting at a very low level with IPLD. And in this case, I start with a value, hello world again, and I might want to take that and essentially create an encoding of that as an IPLD structure. And that structure, in the JavaScript case, it includes the value itself. Okay, so I've got hello and I've got world. But it also includes the canonical byte encoding for that using DAG CBOR, which is an encoding or a codec that we can use to encode the data that we actually care about. And so if I did this, or you did this, or someone else did this, we'd all end up with the exact same encoding, with the exact same CID, because it uses SHA-256 as the hash, and it uses CBOR as the codec, and we're all really happy because we know how to interoperate. But here's what's really neat and really nice about IPLD is maybe in your application, you want to ship data around as JSON because you're a web developer and that's the sort of thing that you speak. But I'm operating in a Rust-based environment and I want to use CBOR because it's a binary encoding and maybe that's nicer for me to think about. Well, you and I can completely interoperate because at the end of the day, we're talking about a higher level IPLD data structure, and it doesn't matter which encoding I initially use, as long as I tell you what encoding I've used, which IPLD helps us with. It's sort of a self-describing data structure in that sense. Then I can ship you JSON CBOR, and you could decode that into, JSON IPLD, and you could decode that and then encode it back into CBOR, and we can move all these things around in different data formats so that you can hyper-optimize for your particular application. And at the end of the day, we'll get different CIDs because we're using different encodings, but the same underlying data we can always play around with and we can always access. So encoding is a pretty important part of how we actually interoperate with IPLD. And IPLD gives us a lot of control over how we actually represent our data structures. And I was kind of getting at that with the first Helia examples. Here's another example using IPLD a bit more directly, where we take that exact same example where I take a value, I encode it into a block, I then make a pointer to that underlying data using its content ID, I encode that, and then maybe I transmit that using my super awesome peer-to-peer chat protocol. And so, hypothetical wire or storage protocol that I'm using to transmit data. Maybe I, transmit the raw bytes. Maybe I transmit the CID, and then I get you to fetch the bytes over IPFS. However I want to ship this information around, we've got a canonical sort of representation of it that we can talk about. And then on the other side, I might actually then go be able to fetch it. And I can do this fairly lazily, which is a pretty nice feature of linked data. And it's kind of like when you click a link on a website, you don't load all of the internet all at once. You just load the little bits that you're looking at any given time. IPLD is no different and adds that sort of capability right into your underlying data structures. So here is an interface or an API that IPLD supports, which allows you to just, for a given chunk of given piece of IPLD data, I want to just go through all of the links that it contains. And I don't want to have to think about I don't need to know that the link was under something called pointer. IPLD just exposes all of the links in a sort of agnostic interface. So I can get a chunk of data, and if I know it's IPLD, I just say, okay, give me the links. Or for each link, I want to go fetch the underlying data that link represents. So I have a lot of control over how I actually access and interface with that data. And if you've ever looked at, say, IPFS data over an IPFS gateway, and it contains links to files, this is essentially what you're doing. You're traversing those links, and the gateway is actually going out, finding all of the links and putting them on the page for you to click on. So in this case, I can walk a given piece of given IPLD data structure and use some hypothetical fetch block by CID function to go and fetch the block and maybe keep a tally of all of the chunks of data that were in the data structure I was parsing, or whatever I might want to do. And so you can lazily fetch data, and you can sort of expose these generic APIs in ways that make it really flexible to build applications on top of. So we can get kind of lazy, and that's what developers want. We want to be as lazy as possible and get the things done that we need to get done. And so I want to keep this talk pretty short. I have lots of time, a little bit of time left for questions, but I'll finish up with, okay, this is great for like sort of static data. What about dynamic data? And so this is a warning, this is a bit of a shameless plug, but I work for a company called Tableland Textile. We have a product called Tableland, and Tableland is specifically for that like next phase where you have like highly dynamic data that you want to be able to query in dynamic ways. So it's like a cloud database that's decentralized, and that plays really nicely with IPFS and with IPLD and with CIDs and fetching and things like that. So imagine like a fully compliant ACID database or ACID compliant database where you can do things like, you know, inserts and updates and selects and queries and fetch this, where that kind of stuff, but all mediated by blockchain, smart contracts, and things like that. So you could do crazy things like only allow users that own my particular NFT to insert a row into a table, for instance. And then select that out, and by the way, there's a row, or there's a column in that row that represents the user's profile picture, and I want you to go and fetch from IPFS that profile picture while you pull that query out of the database, and crazy stuff like that. Pardon me. So this network is live on a bunch of different blockchains. If you are a hacker, chances are you're using something like Polygon or Optimism or some testnet. Tableland is there. You can play around with it. You can mix Tableland with IPFS. You can do all sorts of fun things, and I highly recommend you do that and play around with it. And you know, here's an example of how you might do that from JavaScript inside of your application. And as you can see, it's pretty much just SQL queries and SQL statements and things like that. So imagine a world where you can like sort of hyper optimize the underlying data structures that you are using, encode that into some binary representation, stick that into a table to index it, and then be able to query and slip and slice and do whatever you want with your data, so that you can write an application kind of in the way that you would want to write an application. So shameless plug over. Go check out tableland.xyz for some docs and things like that. Thank you for coming to my talk. Hopefully you've learned something new about IPLD and how easy it is to optimize your developer and data structures while you're building your next hack, this next hackathon. Thank you very much. And yes, it's just me up here, but if there are any questions, and they can be like beginner questions too. That's what this session is kind of all about. So put up your hand, and if you don't have any questions, it will make me look bad, so one question would be great. Yes?
You mentioned that we can use IPLD to access various data sources. I have the idea that if the data source is outside of IPFS, like the Bitcoin blockchain or something like this, you can reference the data, you can reference a transaction or maybe a block, I don't know, but you cannot actually access it unless you have something that, I don't know, a miner or something like this, that can access this piece of information, this piece of data.
Yes, that's a great question, great point. Yeah, so you can reference things with IPLD, and that's all well and good, but you can't access it unless you have some way to resolve that reference. So that's the key piece there. And lots of people have built like IPLD resolvers for like Bitcoin and Ethereum blockchains, and even Git and other like sort of linked data structures that you might be interested in. But at the end of the day, you need that I think I had, you need that fetch block by CID resolver at, you know, in the loop at some point in order to actually go get the data. But the kind of fun thing here is, and this is something that certain apps and applications have used as a sort of feature of IPLD, is you can reference data that isn't actually available, but could be available in the future, as long as you know ahead of time what that thing is going to, like the content of that thing. So a great example of this, because that was very kind of like opaque response, but a good example of this is sort of in a world of like commits and attestations and things like that. So maybe you want to reference some signed document or contract in some data structure that you're working with, but you don't want to reveal the contents of that document right now because it's not relevant, or because you want to keep that information private or whatever. But what you can do is you can say, okay, like in the future, if something comes up, someone violates the contract, we can say, look, here's the contract, and you can verify that it is the contract that it should be by looking at its hashes and all of its links and things like that. But I'm only going to reveal it when we actually need to like implement the contract or like bring it up or something like that. So there's, or you know, there was a chat application that allowed you to share photos, and but you didn't want to necessarily put the photo on IPFS to be publicly available. So you can reference the photo and then do like a direct peer-to-peer connection to actually share the photo itself. So that resolver piece, you know, can be kind of taken out of the loop or customized or changed in a way that you don't get with just putting things on IPFS. But thank you. That almost felt like a setup, but that was a great question. Yeah.
Thanks.
Okay, that's pretty good. Thank you very much. Thanks for coming.